Right, go ahead, Malachi. Show us Fleming's right-hand rule there. Yeah. Force going so, right? What he doing wrong?
So,
His fingers should stay like this, right?
so that's not
Right.
I'm showing you where all coming in.
I want to make sure everything's right. Magnetic field, correct so far, right? So current come in, out, out is up. Right, now take a little while before you get it.
That's not. I like to explain myself when I'm doing it.
Right, you didn't look as confident, but you get.
How much you get?
Look how smooth it is on. Oh, good job. Good job, William, right? So that's the way we use Fleming's right-hand rule, right? And the right-hand rule is used to find the direction of the current. That's okay?
Yes, sir.
Right. We have two other laws to learn, not laws like this, but there are laws that are going to explain how a generator works. So I want you to head up Faraday's law and Lenz's law. Faraday and Lenz's law. Lenz's and Faraday. Right? Faraday and Lenz's law. Alright, so we started with Faraday's law. Head up Faraday's law.
I'll bring tomorrow. Okay. This is? No, they're not. Oh, yeah, that's what? You probably almost fall down.
Right, to head up Faraday's law. Right, so next we how the laws work and then I'll give you other. Okay. Right, so what you see? So I want to explain how this works. So Faraday's law, here's what Faraday's law said. I mean, you'll actually saw Faraday's law. Around the magnet, there's a magnetic field, correct? And the magnetic field moves from north to south. Are you okay with that? Yeah, okay with that? So this magnet, if I were to move this magnet in and out of this conductor, what will happen? This conductor will cut these three lines, right? And as we saw in the simulations, we saw that when a conductor cuts P lines, current is induced. Remember that? Okay, so Faraday said. Faraday said that the rate at which this conductor cuts these P lines is proportional to the amount of current being induced. So if I take this magnet and I move this magnet in and out here real fast, the current values here are larger. Right? You got to remember that when we had the windmill, right? And the faster we put the windmill, the greater the current being induced, right? So the faster, the faster that these P lines cut the conductor, the bigger the current reading. So the galvanometer will give you bigger readings. That's okay. If you bring it in and out slowly, then the galvanometer reading won't be as large. You okay with that? So Faraday said the induced EMF is proportional to the rate at which these P lines cut the conductor. That's Faraday's law, right? Lenz's law is the hard one, right? Lenz's law gives us an idea of direction, right? You see current flowing in here, but we don't know the direction it's flowing in. But Lenz's law allows us to figure out that direction. And here's how it works, right? So Lenz's law basically said, I'll give you the definitions in a little while, but Lenz's law basically said that the direction of the induced current always opposes the motion, right? So what you say? If the magnet moving inwards, right? Opposing the motion means what? This one and push it outwards. Okay. So what magnetic pole has to be formed here to push this magnet back out? North. Very good. A north pole. So a north pole here will push this magnet back out. Correct? If here is north, then here is, and magnetic fields will leave the north and go into the south, right? Right. So here's what we need. We need to figure out current direction. So we're going back to the right-hand grip rule. Right-hand grip rule to figure out current direction. That's okay? So your thumb points towards magnetic north, right? That's for the solenoid, right? So your thumb will point towards magnetic north. So look at my thumb here. My thumb pointing towards magnetic north and current going in at the top and coming out at the bottom. In at the top, out at the bottom. Right? In at the top, out at the bottom. That's okay? So the currents coming, going in at the top here and coming out here. So the current going in at the top and then coming back out here. It's going in here, coming back out. It's going in here, coming back out. So it's flowing like this. Right? And if it's flowing like this, the galvanometer will follow the direction of the current. That makes sense? So how do we figure out current direction? Well, if the magnet moving in, you want to oppose the motion. North will oppose north. If here is north, we use Fleming's right-hand grip rule. Your thumb points towards the north, and your fingers will point current direction. So your fingers going in at the top and coming out at the bottom. Okay? So it means that current going in at the top and coming out here. In, out. That's okay? And you follow it. And once you know the current direction, the galvanometer will follow it. So if current going this way, the galvanometer will go the same way. All okay with that? Yeah? All okay with that? Let's see if we can apply it here now. let's change the direction. So instead of the magnet going in, the magnet will go out. Right? Malini, what pole do you expect to be formed here? You want to oppose the motion. So if it's going out, you want to pull the magnet back in. So it has to be a south. Okay? If here is south, then here is north. Then what you're going to do? Fleming, right hand rule, point towards the north. Malachi, why on your foot? Who's that? Who? Take it off. Right. So yeah. So anybody ever watch videos on YouTube? Like which name you hear the most? And you say Malachi the most?
Yeah.
Right?
What? That's not. Oh.
Every class that I be talking to Malachi. Right. Anyway. So as I said, you use any rule, right hand rule, right? Thumb towards the north and look at the fingers. Look how the fingers behaving. Right? The fingers coming out at the top and going. Right. So it coming out here and going in here. Okay. So it will go, it coming out here and it going in here. So it's going this way. So the galvanometer will follow it in this direction. Are you okay with that? Yeah. So Faraday's law gives you an idea of how large the current is. Lenz's law gives you an idea of the direction. Okay. Draw these diagrams and we're going to give you some notes on those two laws.
Yeah.
All right, so Joy to log online. You're following them, Cameron. So to find the direction, you use the right hand. Yeah, you use the right hand grip rule to find the direction of the current. Right? Not this one, huh? Not the right hand rule. Not Fleming's right hand rule. So using the right hand grip rule. Right? So once you see a solenoid, you're using the solenoid rule basically. Sometimes you just follow the solenoid rule so you don't mix it up. If you look at your fingers, they're looking like a solenoid, right? Almost half past 12. Well, I think I right time already. So you all recognize that magnets have a lot of theory, right? It's mainly theory that we did. The calculations is what we'll do in transformers. Right? But there's a past paper that I will show you just now. That looks just like this. They have a magnet here to show you direction it's moving in. And you have to fill out the rest. Okay? Ready for note? Ready? Faraday's law. Faraday's law gives an idea of the magnitude. Faraday's law gives an idea of the magnitude. Faraday's law gives an idea of the magnitude of the induced current. Gives an idea of the magnitude of the induced current, while Lenz's law gives an idea of the direction, while Lenz's law gives an idea of the direction of the induced current. Of the induced current. So in your summary, you should have Faraday gives you magnitude, Lenz gives you the direction. All right, you should that's what you'll use to remember it, right? Full stop. Faraday's law states that. Faraday's law states that. Faraday's law states that the magnitude of the induced current, the magnitude of the induced current the magnitude of the induced current is proportional. The magnitude of the induced current is proportional to the rate at which the conductor cuts the magnetic field lines. To the rate at which the conductor cuts the magnetic field lines. To the rate at which the conductor cuts the magnetic field lines. Full stop. Right? So in short, Faraday's law is what? Faster the field lines, faster the conductor cuts the field lines, the bigger the current. Okay? So because it'll be hard for you to memorize this thing word for word for sometimes. Some people can do it, but if you can't, always have a visual image of how it works, right? The faster this moves in and out, the bigger the current here, right? You might remember that, right? And number two, Lenz's law. Lenz's law states that Lenz's law states that the direction, underline direction, Lenz's law states that the direction of the induced EMF, Lenz's law states that the direction of the induced EMF is such that it always it always opposes motion. It's such that it always opposes motion. Okay, those are two laws. All right. We need to come here and explain what happened, right? So I want to just give you an idea of how to remember this. Number one, right? Number one, if a magnet moves inwards, sorry, if the magnet moves inwards, number one, a knot is produced. Not produced, right? A knot is produced to oppose motion. Remember, it's moving inwards here, right? Number two, give it up. A knot is produced to oppose motion. Number two, use a right hand grip rule. Use right hand grip rule to find current direction. Right, use right hand grip rule to find current direction. And number three, galvanometer. Take two markers off.
Mil. Posso parar de colar ali. Ah, você deixa que eu morri. Do player boy.
Alright, write down those 3 points there, please.
Eu gosto, né? Isso aí, parceiro.
Hey. Copy down this one, please. Right, 1, 2, 3. 1, 2, 3, and then you do a 1, 2, 3 here as well, right? Same thing. Okay. The only problem, anyway, right? For homework, I want you to draw a generator, simple diagram, one that you can handle. For homework, draw a generator and explain how it works. Homework, draw a generator and explain how it works. Just like it's similar to the motor, except no current. Next class. Next class is what? Oh, today is Tuesday. Okay. Anyway, we're not done here. Write down 1, 2, 3 here for me as well. This 1, 2, 3 is for the first diagram. Here. Do the same thing here. And I want to show you the past paper that came in this. Huh? Malachi has no more work now. Gosh, by Malachi has no more work now. Ravi,
I tried to my work here.
just take Ravi phone.
Yeah, but I don't have ship phone. I don't have no phone. I said, I don't have your phone. That don't make a difference.
Call it and see.
So what? We put on my flashlight.
What's your number? What's your number? No. What's your number?
I.
Submit forward. Keep clicking it over. I didn't create your group yet. Right. So let's take a look at the past paper, how it looks, right? So watch here. Kevin, a physics student, conducted an experiment to determine the effects of electromagnetic induction. He uses the following apparatus, right? What does electromagnetic induction mean? Exactly what you see in there. He uses a magnet to induce current. Personal, you okay with that? So electromagnetic induction is taking a magnet to give it to induce electricity. That's okay? Oh wait, this is exact same thing. That was south and north. Anyway, so watch this here. The magnet is pushed into the coil with the north pole entering first. Draw on figure 1 the direction of the induced current. What direction will the current be in? I'll tell you. Look at the diagram. What direction would it be in? Okay, tell me what direction the galvanometer will move. To the right, to the left. To the left. Yeah, correct. Like the answer on the board. The answer on the board. Here will be north, here will be south as it moves inwards. And the current will go in this direction. Oh, wait. Enter right in there. You all seen any writing there online? On the screen? No? Oh, shucks. All right, by diagram changing. Okay, now, yeah, I've seen it now. Right, so the current will go like that, just like the one on the board. Everybody okay with that? Yeah? Everybody okay with that? Faith? Quinn? Are they okay there? All right, so how much marks was that? That was another 2 marks there. Why is the current being induced? So let's see if anybody learned anything. Why is the current being induced as you put the magnet in and out? Right, because the conductor cutting the field lines and by Faraday, current will be induced. Okay. Why is it necessary to have a sensitive galvanometer? Because you all think the current value will be large? No. So you need a sensitive galvanometer because the current value is small. And last one. Tell me what will happen here. What direction current will move in here? Let me ask somebody online. Maria, what direction will the galvanometer move here? Right, it's moving out, right? What direction will it move? Maria? Somebody can help Maria there. Shannon, what direction will the galvanometer move here? To the left. No, but actually to the right. Right, because here will be south and here will be north. The answer on the board is Shannon. You're okay with that? Everybody okay with that? Malini, are you okay with that? Yeah? Last question. Last part 5. State 3 changes or adjustment Kevin can make to give you a larger EMF. EMF simply means current. What are 3 adjustments you can make? Let me see who's thinking. 2 you can figure out. 1 might be tricky. What are the 3 adjustments that you can make to let the current value be larger? Right. Move in and out faster. So somebody say the next one there. Right, very good. Larger magnet. One more. One more. Huh? Am I here, Quinn? Yeah. All right, so yeah, we got next one before we take it in the wrong way. Right? Reset to wrap more wires around the coil. So basically more turns. Right? Number 3, you want more. Number 3 is more turns on the coil. All right. So those are the 3 things. So your homework, all I want you to do is to draw a generator and explain how it works. Okay. All right. Nice job, Olive. All right. So good. We're almost done with this part of magnets. So you'll get